おはようございます。お元気ですか？コロナウイルスは、とても怖って心配するけれども、手を洗って、うちにとどまってすれば大丈夫になると思います。あえっと、ブースマン先生、今日のレッスンを教えてください。All right, let's get started. All right, good morning. Here we are on Wednesday. We're halfway through our second week of this new experience. I hope you're doing well. Announcement to start our day. Your exit ticket today, due by midnight, will be to submit a question you have from today's lesson. Again, if you don't have one, then I ask you to think of a question someone might have about today's content and submit that as your question, okay? We are continuing section 10.5. Again, 10.5 is all about convergence. Remember that a series is really only useful to us where it converges. Yesterday we talked about the center and the radius of convergence and the interval of convergence and what those three separate things actually mean. We've actually learned a couple of convergence tests already. Remember, the first was the nth term test. And this told us that if the limit as n approaches infinity of the nth term of a series equals 0, or I'm sorry, does not equal 0, then the series diverges. Okay. And conceptually, remember, this is saying that if there's not some point in our series that we start adding 0, then our sum is just going to continue to grow, so it will never actually converge upon any specific value. We also talked about geometric series. Okay, now there is a clarification I want to make from yesterday. I did leave out something very important. That a geometric series converges if and only if the absolute value of the common ratio is less than 1. So it's the same kind of idea that each term ends up getting successively smaller and smaller and smaller, and so we will eventually, as we approach infinity, start adding an infinitely small value. So we will actually converge, we'll stop our sum at some value. Okay, if that common ratio is between -1 and 1, remember these are equivalent statements, then our series converges to a over 1 minus r. Otherwise, it diverges. So if this is not true, then our geometric series will diverge. It will continue to grow to infinity. The third test I would like to talk about is known as the alternating series test, commonly abbreviated AST, the alternating series test. If we have some series from n equals 1 to infinity of -1 to the n plus 1 power times some u sub n. Okay, what does this actually look like? So that means our first term is going to be positive, minus our second term, plus our third term, minus our fourth term, and so on. Okay. Then this series will converge if we meet three criteria. First, each term is positive. Now, I'm sorry, not each term, but if we ignore that alternating sign, okay, this u sub n that's left over, that must be positive in each term. Okay, that's our first criteria. The second, as we go to infinity, then each successive u sub n term is less than or equal to the one that came before it. Okay. And our third criteria, the limit as n approaches infinity equals 0. So let's think about what taken together all of this is saying. So this part is positive, so that means that we're not dealing with anything other than this alternating sign. It's not like sometimes this part of our term is positive and sometimes it's negative. That is always positive, and so it is just a very straightforward alternating sign for the entire series. Okay. Each successive term is less than or equal to the one that came before it. Again, that's ignoring that alternating sign. So, for example, we have 1 minus 1/2 plus 1/4. So each of those terms is less than or equal to the one that came before it. And then we have the limit, this is basically the nth term test, okay? The limit as we go to infinity of each of those u sub n pieces of the terms equals 0. So at a certain point, okay, that number will get small enough that it's infinitely small, okay? And we start to add 0 to our sum. If all three of these things are true, then our alternating series will converge. Notice this is a very specific use case. Our series has to look like this. It must be alternating. Now there is some flexibility. We can have -1 to the n plus 1 power. This could also just be -1 to the nth power. Okay, so then it would start negative, positive, negative, positive. The point is that it is alternating sign for the entire series. Doesn't matter what we're starting at. Taken together, all three of these criteria mean that it's basically the same idea that we've discussed with the nth term test and geometric series and so on. That, all right, the sign is alternating, but each term is getting smaller, okay? And eventually we're going to start adding an infinitely small value to our sum, to our series, which means that our whole series should converge to a specific value. If any one of these three things is not true, then our alternating series will not converge. I want to spend today going through two examples from the second page of our mastery sheet, 10.5. And then I'll ask you to finish the other couple of problems there. So let's look at the first series. This is, it's kind of given away by the fact that this is an alternating series test problem. This is an alternating series. We know because we see this -1 to the nth power that tells us that our sign is going to alternate for the duration of the series. And we have to show those three things. Okay. We need to show that each u sub n is positive. So again, that's ignoring this alternating sign. So in this case, u sub n is 1 over n factorial. This is always positive for this particular series. There's no value we can plug in for n that would make this negative, okay? Starting at 1, going to infinity, this value is always going to be positive, whether we're plugging in 1, 10, a million, all the way to infinity. So this is true. Okay, our second criteria. Here's where things get a little dicey. We need to show that each successive term is smaller than the one before it for the entire series. Okay. In other words, let's use the actual value that we have for this series. U sub n is 1 over n factorial. And we need to show that 1 over n plus 1 factorial is always less than that. Okay. Now, this idea, what I'm about to do, is going to bleed into the next convergence test that we look at starting tomorrow. But for now, okay, I like that we're kind of introducing it here. We want this term to be less than this term. Another way of looking at that is to say is this ratio, is this fraction of u sub n plus 1 over u sub n always less than or equal to 1? Okay. Because if our next term is always less than the term before it, less than or equal to the term before it, then this should always be true. Okay, we're never going to get a bigger number on top than on the bottom. Okay, so we want to show, basically, taking these two things together, that 1 over n plus 1 factorial over 1 over n factorial is always less than or equal to 1. Is this always true? Well, we need to simplify this a little. Okay, and I've run out of a bit of room here, so I'll come up over, I'll do it down here. This is 1 over, now n plus 1 factorial, let's think about this. That's n plus 1 times n minus 1 times n minus 2, all the way down to times 1. N plus 1 times, okay, let's think, n times n minus 1 times n minus 2, all the way down to times 1, itself is just n factorial. So n plus 1 factorial is just n plus 1 times n factorial. We're dividing this by 1 over n factorial, which means we're multiplying by n factorial over 1. The n factorials cancel, and this is 1 over n plus 1, which, for all values of n from 1 to infinity, is always less than or equal to 1. So this is always true. And we can test this. Plug in 1, we get 1 over 2. Plug in 10, we get 1 over 11. That is always less than or equal to 1, no matter what value of n that we choose. Okay. So we've shown 2 of the 3 criteria are valid. Let's look at the third. Does the limit, as n approaches infinity, of 1 over n factorial equals 0? Well, plug in infinity, and we get 1 over an infinitely large value, which indeed is 0. So because we meet these 3 criteria, this series converges. Okay. Pause, go back through any part of that you need to. This right here, again, this idea of testing this ratio is going to be very important for tomorrow's lesson, but for now, really try to understand what we just did here, okay? Why that shows what we wanted it to, okay? The other 2 parts should be fairly straightforward. All right, finally, I'd like to look at the very last problem here. Actually, I want you to do all the other 3 problems on this page. Use what I just did as a template. I want you to work through numbers 2, 3, and 4 today. That will be your work for the day. You're not submitting it, okay? I'm not checking it as a problem of the day, but if you want to understand the alternating series test, then you're going to work through these. Please submit any questions you have through the exit ticket, and of course, join our Google Meet if you need me to work through any of those other 3. I'm more than happy to do that together, okay? Otherwise, please reach out if you have any other questions. Have a great day.
今日のレッスンが終わりました。じゃあ、どうもありがとうございました。また明日。